good evening. Today is week 9 of the live interactive session, Introduction to Atmospheric and Space Sciences. If you guys remember, last class we were discussing about the stability of the atmosphere, different conditions determining the stability, Brent-wise solar frequency, etc. So today we will continue whatever discussions we were having in the last class. So last class we derived the formula for the vertical acceleration of an air parcel, which was given by So last class we derived the formula for the vertical acceleration, which was given by z double dot is equal to minus g by tv into gamma v dash minus gamma v is equal to into dz. So where tv is the virtual temperature, gamma v dash is the lapse rate of the parcel, and gamma v is the lapse rate of the environment. Z double bar is just the acceleration, which is basically d square z by dt square. We are dealing with z because we are discussing vertical motion of the air parcel. Since vertical direction, that's why we are using z. So this is the equation that we derived in the last class, and from this we found out that this is of the form. This equation is basically of the form z is equal to minus n square dz, where n is given by root of g by tv into gamma v dash minus gamma v. The equation is of this form, which is of the order of a second order. This is of the form of a second order differential equation. Which is having solutions in the first case. So this is the equation that we have, second order linear differential equation. A square z by dt square is equal to minus n square dz, where n is given by g by tv into gamma v dash minus gamma. So in this case, when n is positive, the solution of this equation is of the form z is equal to a sin nt plus b cos nt. This basically represents the parcel as having stable oscillations. So the z is actually having a motion like a sinusoidal wave kind of thing. So it just means the parcel is actually oscillating with respect to its mean position. So which means the parcel is basically stable. Now the second case was that when n was negative. So if n is negative, the above equation becomes d square z by dt square is equal to n square dz. In this case, so this is the first case. This is the second case. So in this case, the solution will be z is equal to a raised to plus or minus n into t, which means the parcel is having, if the parcel is displaced, it will keep on moving in that direction, just kind of having an exponential, um, like the displacement is keeping on increasing. So that's what this says. And when we look at n will be the value of n is negative. Since it is a square root, it means n becomes imaginary. So in the first case, n is having real solution, whereas in the second case, since it's a square root, n will be having imaginary solution. So in the first case, as we can see, if we are telling that n is positive, it basically means gamma v dash minus gamma v is positive. So we know n is basically root of g by tv into gamma v dash minus gamma v. So only when n is positive, we are having real solution. So when n is positive, it basically means gamma v dash minus gamma v is positive, which implies gamma v dash is greater than gamma v. This lapse rate of the parcel is greater than lapse rate of the environment. So here, if this is the temperature and that height z, this is, if the profile will be like this. This is gamma v, this is gamma v dash. The parcel will be having, if we take any particular point at one particular pressure level, this is the temperature of the parcel, sorry, temperature of the environment, whereas this is the temperature of the parcel. The temperature of the parcel is less than the temperature of the environment. The parcel, so since the parcel is cooler than the environment, it means it will sink. Cooler in the sense it will be denser. It is denser, so it will sink. So that is the first case. So when n is positive, we are having real solutions to the second order differential equation. So n is positive basically means the lapse rate of the parcel is greater than the lapse rate of the environment. So parcel is having a higher lapse rate. It basically means at any particular pressure level, the temperature of the parcel will be less than the temperature of the environment, which means the parcel is cooler compared to that of the environment, and the parcel will be denser and it will have a tendency to sink. Now the second case, so this is case 1, when n is positive. Now the second case, case 2, when n is negative. So n is negative means the square root will be negative. N is basically the square root of g by tv into gamma v prime minus gamma v. negative comes within the square root, the solutions are basically imaginary. So n becomes negative in the sense gamma v dash minus gamma v will be less than 0, which basically implies gamma v dash is less than gamma. So if we look at the slope, this is the temperature, this is the height set. Suppose this is gamma v, this will be gamma v dash. Gamma v is greater than gamma v dash. So if we take at any particular level, this particular level, this is the temperature of the parcel, and this is the temperature of the environment. So gamma v dash is less than gamma v, and if we consider the temperature at any particular level, it is seen that the temperature of the environment is the temperature of the parcel is greater than the temperature of the environment. So this is the temperature of the parcel, and this is the temperature of the environment. So at any particular pressure level, temperature of the parcel is greater than that of the temperature of the environment, which basically means the parcel is warmer than its environment, means it is lighter, the parcel is lighter. If it is lighter, the parcel will rise in the atmosphere. So the parcel will rise in the sense if the parcel is displaced from its initial position, it will keep on moving in the displaced direction. So this is the condition for, this is basically an unstable. So in this case, in the stable case, when n is positive, this is stable, n is greater than 0, displaced parcel oscillates about mean position. That is the condition for the stable case, whereas in case of unstable case, when n is less than 0, n is imaginary, it is seen that the displaced parcel continues to move in the displaced direction. So that is the second case. So to summarize, based on the lapse rate, so two cases we saw. First one was n greater than 0. Second one was n less than 0. So in this case, when n was greater than 0, it meant gamma v is greater than gamma v dash is greater than gamma v, and when n was less than 0, it was seen that gamma v dash is less than gamma. So two conditions based on lapse rate, if we write, gamma v dash can either be greater than or less than gamma v. If it is greater than gamma v, it means it is stable, the parcel is stable, parcel oscillates about its mean position, whereas gamma v dash is less than gamma v. it means the parcel is unstable. The parcel will keeps on moving in the displaced direction. And there is a third case when gamma v dash is equal to gamma v, which means it is neutral. Now if we write in terms of temperature, we have temperature of the parcel is either greater than, at a particular pressure level, is either greater than or less than the temperature of the environment. So in stable case, the temperature of the parcel is less than the temperature of the environment, which means parcel is denser, so it sinks. Second case, temperature of the parcel is greater than the temperature of the environment. So this is stable, this is unstable. So in this case, the parcel is warmer, so it will be lighter or less denser, it will rise. And the third case is the temperature of the parcel is equal to the temperature of the environment. That case is neutral. So based on the value of n, based on the value of lapse rate, and based on the value of temperature, we know how can we define stable, unstable, and neutral atmosphere, or neutral conditions. Now, this gamma V that we talked about is basically the environmental lapse rate, right? Sorry. And this gamma V dash that we are telling, which is a parcel lapse rate, so we have already learned three types of lapse rate. Just a second. Just a second. Yeah. We are already familiar with three types of lapse rate, which was environmental lapse rate, which is having a value of around 6 degrees Celsius per kilometer or 6 Kelvin per kilometer. Then we know tri-adiabatic lapse rate, which is basically G by Cp, which was having a value of 9.8 Kelvin per kilometer. This was derived for parcels that are unsaturated. Then we also learned something called as saturated adiabatic lapse rate, which was having a value of around 4 to 5 degrees Celsius per kilometer or 4 to 5 Kelvin per kilometer. This is basically the lapse rate of the parcels when it becomes saturated. So environmental lapse rate is basically our gamma V. So this tri-adiabatic lapse rate is basically gamma D, and saturated adiabatic lapse rate gamma W. So gamma V dash, which is basically the lapse rate of the parcel, can either be gamma D when the parcel is unsaturated, and it can be gamma W when the parcel is saturated, right? So it can either be gamma D or dry adiabatic lactate when the parcel is unsaturated, and the value of gamma gamma V dash can be uh, gamma W or saturated adiabatic lactate when the parcel is saturated. Now based on this, so now we have 3 lactate, right? So this is set. This is temperature. We know the value of dry adiabatic lactate, which is around 9.8 Kelvin per kilometer. So this is gamma D, which is 9.8 Kelvin per kilometer. And then we have gamma W or dry adiabatic lactate, which is 4 Kelvin per kilometer. Suppose the environmental lactate is somewhere. So this environmental lactate which we are telling that is having a value of 6.5 Kelvin per kilometer is a variable quantity. It can vary depending upon the meteorological or atmospheric condition. It is not a constant. Okay. So suppose now we are considering a condition where the lactate is actually greater than gamma V is greater than both gamma D and gamma W. That is, the environmental lactate is having a value which is greater than dry adiabatic lactate and saturated adiabatic lactate. So this is how the lactate is increasing. Lactate increases in this direction. So we are considering a case 1, when the value of environmental lactate is greater than dry adiabatic lactate and saturated adiabatic lactate. So which basically means our gamma V, so this is gamma V dash, right? Gamma V is greater than so which basically means gamma V is greater than gamma V dash. What does this basically? If the environmental lactate is greater than the parcel lactate, this condition is basically unstable. We already learned that, right? If environmental lactate is greater than the parcel lactate, which means the parcel is unstable. So this is the condition of instability. Now the second case is, let us consider the value of gamma V is actually less than both. This is case 2. This is case 1. So in this case, the value of gamma V is less than both gamma D and gamma W, which basically means gamma V is less than gamma V dash. So this we already learned is basically a stable condition. Gamma V is less than gamma V dash is basically a stable condition. Now let's assume a third case in which the value of the environmental lactate or gamma V is actually in between gamma D and gamma W. So the case 3 is when the value of gamma D is greater than the value of gamma V is greater than gamma D, but it is still less than gamma W. So this case in which so in this case it can either be stable or it can either be unstable, right? So suppose if the parcel is saturated, it means gamma V prime is equal to gamma W. And this condition matters. So gamma V is less than gamma V prime. This is the condition for gamma V is less than gamma V prime. This is the condition for stable. This is basically stable condition. Now, if the parcel is unsaturated, if it comes in bit, just a second. If it is coming in between, gamma D is having the highest value and gamma W is the lowest. So gamma W greater than gamma V greater than gamma D. That will be the condition. Gamma D is the highest. Right? So it will be gamma W greater than gamma V greater than gamma D. As we can see from here, the lapse rate is increasing in this direction. So gamma D is having we are discussing the third case when the lapse rate of the parcel, the environmental lapse rate is falling in between the dry adiabatic lapse rate and the saturated adiabatic lapse rate. So in that case, we can see gamma D is the highest, is having the highest value, followed by the environmental lapse rate and followed by the saturated adiabatic lapse rate. So it will become gamma W, which is the lowest. Gamma W is greater than gamma V greater than gamma, sorry, less than. Yeah, gamma W is the lowest. Gamma W less than gamma V less than gamma D. Right? Yeah. So now, if the parcel is saturated, it means gamma V dash is equal to gamma W, and from the condition we can write gamma V prime is less than gamma V. Yeah. Gamma V prime is less than gamma V, which basically means the environmental lapse rate is higher compared to that of the parcel's lapse rate. It means the atmosphere is unstable. Unstable. Now, if the parcel is unsaturated, it means gamma V prime is equal to gamma D. So it will be gamma V is less than gamma V prime, or gamma V prime is greater than gamma V, which is basically stable. So the parcel may either be stable or unstable based on if it is saturated or unsaturated. So if the parcel is saturated, then it becomes unstable. So when the parcel becomes saturated, it will follow the moisture adiabatic lapse or the saturated adiabatic lapse rate, whose value is less than that of the environmental lapse rate, which means the parcel will become unstable. And if the parcel is unsaturated, that means parcel is unsaturated in the sense the lapse rate of the parcel will be equal to that of the dry adiabatic lapse rate, and the environmental lapse rate is less than the parcel lapse rate. Sorry, the parcel lapse rate is actually greater than the environmental lapse rate, which basically means the parcel will be stable. So when the parcel is unsaturated, then it becomes stable. So based on the moisture content in the parcel, or based on whether the parcel is saturated or unsaturated, the condition for stability changes. This particular condition is known as conditionally stable or unstable. What is the condition? Whether the parcel is saturated or unsaturated. So based on whether the parcel is saturated or unsaturated, it becomes stable or unstable. So this is basically known as conditional stable or conditional unstable. What is the condition for conditional instability? Gamma W. The environmental lapse rate should fall within the values of dry adiabatic lapse rate and saturated adiabatic lapse rate. It should be less than the saturated adiabatic lapse rate, and should be greater than the saturated adiabatic lapse rate and less than the dry adiabatic lapse rate. So that is the condition for conditional instability. I hope it is clear. Now let us look at some energy terms such as convective available potential energy, or A, and convective inhibition energy, which is known as psi. So we have learned these things earlier. I have mentioned these terms earlier when we were discussing the vertical profile of temperature movement of an air. This is vertical movement of an air. So this is temperature, this is set. Suppose this is the environment lapse rate. So this is how the temperature of the atmosphere is actually changing as we go up in the atmosphere. And suppose there is a parcel which is initially at this position. The parcel was initially lifted by some lifting mechanisms that we have already discussed, like orography, convection, moisture convergence, etc. Suppose due to some lifting mechanism, the parcel was initially lifted to some particular height. Let this be Z1, where it became saturated. Can you tell me what is this height called, or what is this level called? So the level at which the parcel became saturated is basically known as the lifting condensation level. So when the parcel reached Z1, the parcel became saturated. That particular height is known as the lifting condensation level. Until the lifting condensation level, the parcel is unsaturated. It had moisture in it, but it was not saturated, it was unsaturated. So as it from Z is equal to 0 to Z is equal to Z1 is just following dry adiabatic lapse rate, or gamma. So now when it reaches Z1, the parcel became saturated. Now if the parcel is undergoing a further ascent, then condensation will start occurring. And we already know, once it is saturated, it will start following the saturated adiabatic lapse rate. Also, Once condensation starts to begin in the parcel, there will be an additional supply of energy to the parcel, which will start increasing the temperature of the parcel. So, temperature of the parcel will start increasing because of the additional supply of heat, and it will follow a profile like this. So since it is saturated, it will be following the saturated adiabatic latrate or gamma W. And now the region when the temperature of the parcel equals the temperature of the environment, or the level above which the parcel is having a higher temperature higher to that of the environment, is known as level of free convection. So above Z2, the temperature of the parcel is greater than that of the temperature of the environment, which means without the help of an external agency, the parcel can rise on its own. Or we can say above Z2, the parcel is self-buoyant. Okay. So initially from Z is equal to 0, there is a parcel which is having some moisture content, but it is unsaturated. So initially with the help of some lifting mechanism like orography, convection, moisture convergence, etc., the parcel was lifted to a particular height Z1. And at the height Z1, the parcel became saturated. So as the parcel is rising, the temperature of the parcel will start reducing. And even though there is no additional supply of moisture, the parcel will become saturated because the saturation vapor pressure is inversely proportional to the temperature. So as temperature is decreasing, the saturation vapor pressure also decreases, which basically means the parcel will eventually become saturated. So at Z1, the parcel will become saturated. And after Z1, condensation, if the parcel is undergoing further ascent, even above the lifting condensation level, it means condensation will start occurring in the parcel. So now when condensation starts occurring, there is one thing is the parcel will start moving in the saturated adiabatic latrate, which is less than the dry adiabatic latrate, because there is an additional supply of heat due to the conductor vapor of water vapor into water. So after a particular height of the temperature of the parcel keeps on increasing, and after a temperature of the pipe, the temperature of the parcel will become equal to that of the at one particular height, the temperature of the parcel will become equal to that of the temperature of the particular, and that particular level is known as the level of free convection. And above that particular level, temperature of the parcel is always remaining greater than that of the environment, which means the parcel is basically self-buoyant. So we can temperature also we can see from the figure. See LCL. If we look at LCL, this is the temperature of the parcel. And at the same level, if we see this is the temperature of the environment, right? So at Z1, temperature of environment, this is greater, right? Greater than temperature of the parcel. Now what is happening at Z2 or LFC? At Z2 or LFI profile, which is basically showing that of the parcel is coinciding with the environmental profile here, right? So at Z2, T environment equal to T parcel. Now what is happening above Z2? Above Z2, if we take a level like this, so this is the environmental temperature, and this is the parcel temperature, which is greater T parcel greater than T environment, which means the parcel is self-buoyant, and without the help of an external agency, the parcel can rise on its own. So above itself, the parcel will continue to move in the displaced direction. And at this height, which is Z3 or LNB, Z3 is basically known as level of neutral buoyancy. basically known as the level of neutral buoyancy, which is generally the top of the cloud. So LCL is generally the base of the cloud. So this is how the clouds form. Like cumulonimbus, we learned about the different types of clouds in the last class, and we learned there are vertically developing rain-bearing clouds as well. So those were named cumulonimbus clouds. So these are vertically developing cumulonimbus clouds. It will be having a height like this. The base will be at LCL. This is the base of the cloud. And it will rise till Z3 or the level of neutral buoyancy, the top of the cloud. I also told you one thing, that above the LNB the cloud cannot rise because that is almost the top of the troposphere, and above that stratosphere starts. Above that is the stratosphere, and there the temperature is actually increasing with respect to height. So that condition, so it will be difficult for the air parcel or cloud to develop further. So this will be top of the cloud over level of neutral buoyancy. So, and it will generally take an anvil shape because since it can't extend further vertically, it will start extending horizontally, and at the top of the clouds will generally have a shape. So this is a cumulonimbus cloud. Okay. Have there are three different levels. This is the temperature. This is set. This is environmental lapse rate. This is the parcel's profile. So the first level, Z1 LCL, then the second level, Z2 Z1 LCL, level of lifting condensation level, Z2 LFC, level of free convection. After that the parcel is having higher temperature compared to that of the environment. There is a third layer, which is Z3, which is the level of neutron buoyancy or LNB. So if you look at the area within the curve from Z is equal to 0 to Z is equal to Z2, this is the negative area. This area is negative. This area is basically known as psi. And if you look at this particular area, this is the positive area, which is known as cape. So if we write it mathematically, so from surface to LFC, the area within the curve is known as convective inhibition energy, and from LFC to LNB, the area under the curve is known as K, or convective available potential energy. So first one is the convective inhibition energy. Convective inhibition energy sign. This acts as a barrier that we have to reach before reaching the positive energy. So the amount of energy which the particle should be provided to push it up to LFC or Z2. The amount of energy required for the parcel to reach LFC. This our set is basically given by convective inhibition. So E sin is given by integral Z0 to Z2 Z double dot into Z double dot. What is Z double dot? We already know. The vertical acceleration by is given by, we already wrote it initially. Z double dot is given by minus G by TV into gamma V dash minus gamma V into dz. If we take the minus inside, it will become Z double dot is equal to G by TV into gamma V minus gamma V dash into dz. Z double dot is given by G by TV into gamma V minus gamma V dash into dz. Okay. And we know TV is, if we want to write it in terms of temperature, we can write gamma V, gamma V dz, we can substitute as the temperature at a particular height TV is basically given by T0 minus gamma V dz, and in case of parcel it is TV dash is equal to T0 minus V dash into dz. We substitute gamma V minus gamma V dash dz in the equation, it will become gamma V dz is basically T0 minus TV, T0 minus TV minus of gamma V dash dz is basically T0 minus TV dash. So it will become T0 and T0 will go TV dash minus T. So if we write in terms of temperature, it will become Z double dot, or acceleration of the parcel. Vertical acceleration of the parcel is given by G by TV into TV dash minus TV. This is this virtual temperature of the parcel minus virtual temperature of the environment divided by the virtual temperature of the environment. That is the vertical acceleration. Now the energy sign. Convective inhibition energy is basically given by G into integral of from surface Z0 to LFC, right? Z2 or LFC. So sign is basically, as I have already shown, it is from surface to the LFC or Z2. So to integrate from surface to LFC, the vertical acceleration we will get G into TV dash minus TV divided by TV into dz. This is E sign. So up to LFC, we know up to LFC, if we take the temperature of the parcel till LFC, the value is always less than the temperature of the parcel. This is the temperature of the parcel. This level, this is the temperature of the environment. This level also, this is the temperature of the parcel. This is the temperature of the environment. Till LFC, temperature of the parcel is less than till LFC, the temperature of the parcel is less than the temperature of the environment. So since the temperature of the parcel is less than the temperature of the environment, which means TV dash minus TV, or TV dash is less than TV, which basically means TV dash minus TV is negative, or E sign is negative. That's why I told that this is a negative energy. So this is the energy that we have to be, this this much energy needs to be provided for the parcel to cross this barrier of this initial barrier. Once it reaches the level of free convection, without the help of any external agency, the parcel can move by its own. Yeah, it can vertically upwards by its own. This is the convective inhibition energy. Now we have another one, which is the convective available potential energy as well, above LFC till the level of neutral buoyancy. We have CAPE, which is the convective available potential energy. So CAPE is the convective available potential energy. It is the energy available in the atmosphere for the parcel to move or rise further. Energy that is available in the atmosphere for the parcel to move or rise further. So this EK is given by similarly integrating from. So this will be, we will integrate from LNB to LNB. In case of sine, we were integrating till LFC. So this is from LFC to LNB. Z2 to Z3 will be same thing. TV dash minus TV by TV into dz. G. So in this case, above LFC, we know TV dash always greater than TV. If you look here, this is the environment profile. So this slanted line is the environmental profile. So above LFC, this is the temperature of the environment. This is the temperature of the parcel. Temperature of the parcel state. As we go up again, this is environment. This is parcel. It is always still LNB. It is always greater than the temperature of the environment. So TV dash is always greater than the temperature of the TV dash is always greater than the temperature of the environment. Which means this area or E cape is positive. So no need to provide external energy to the parcel for it rise from Z2 to Z3 from level of or LFC to LNB. So there is no need to provide additional energy for the parcel to rise from the level of free convection to the level of neutral buoyancy. So if we have a higher value of Cape, so for the development of thunderstorms and all, that is the most favorable condition for the development of clouds, storm clouds, the cumulonimbus clouds, thunderstorm clouds, favorable conditions are lower value of sine. So the value of environmental lapse rate it should be such that it follows these or it is suitable to these conditions. So the value of sine should be lower and the value of cape should be high. So these are the favorable conditions for the development of big clouds, strong clouds. Lower value of sine and higher value of, so higher the cape, higher the probability of convection and thunderstorm. Thunderstorm. Now this E cape in terms of the vertical. So how to write it in terms of vertical velocity? We will see. So cape. Yeah. So E cape is basically integral of LFC to LNB into vertical acceleration into dz, right? Z double dot into dz is equal to integral LFC to LNB basically integral of LFC to LNB d square z by dt square into dz, right? So this d square z by dt square can be written as d by dt of dz by dt, and dz by dt is nothing but z dot. So d square z by dt square can also be written as dz dot by dt, which is equal to integral LFC to LNB dz dot by dt into dz. Yeah. dz dot by dt into dz. This can further be written as E cape is equal to integral LFC to LNB z dot into dz dot. Yeah, dz dot by dt into dz. This can further be written as z dot into dz dot into dz by dt. If we rearrange this, it will become dz dot into dz by dt, and dz by dt is nothing but z dot. So it can further be written as z dot into dz dot. Now, if we apply the chain rule and do the u dash v, d by dt of u into v, that chain rule if we apply, we will get the z dot into the differential of the second term plus um, differential of the first term into the second term. Finally, if we do the chain rule, we will finally get it in the form integral of LFC into LNB into half of dz dot square. It will come once you do the differential, it will be of the form half into dz by dt the whole square. It will come in this d of half into d of half into dz by dt the whole square. It will come in this form. So once we take the integral, it will become Cape is equal to half into dz by dt the whole square. So it was d of half into dz by dt, integral of d of half into dz by dt the whole square. Now if we take the integral, it will become half into dz by dt the whole square. This is Cape. Now dz by dt is basically the differential of the displacement. It is nothing but velocity. Dz by dt is velocity. Since it is in the vertical direction, we can write it as w. Okay, this is from finite integral. It is from LFC to LNB. So K becomes half into dz by dt LNB minus dz by dt of LFC. Dz by dt the whole square of LNB minus dz by dt of the whole square of LFC. It will become V square. Dz by dt is nothing but V. So V square at LNB minus V square at LFC. Kinetic energy for unit mass. Kinetic energy for unit mass of an air parcel. So Cape will become half into V, or we can put W since it's vertical. W square LNB minus W square of LFC. This is Cape in terms of vertical velocity. From the initial expression that Cape is equal to integral of vertical acceleration into dz, we derived the value of Cape in terms of the vertical velocity. Now let's try to do a problem based on this. It's just a simple problem. Given Cape is equal to 120 joule per kilogram, what will be the velocity of parcel h ln? So we know what is the value of Cape. We want to find the velocity of parcel at the level of neutral bound. So Cape we know is nothing but half into V square LNB minus V square LFC. Let's assume V or W. Let's assume that W square, W at LFC or vertical velocity at LFC is 0. Suppose this is 0, which implies Cape is equal to half into W square LNB. The value of Cape is given, so W square is equal to 2 into Cape, or W is equal to root of 2 into Cape. The value of Cape is root of 2 into 120. How much will be the value of W at LNB? What is the value? Can you tell me? Yeah, the value will be around 15.49 meter per second. 15.5. This value is very high actually. It won't be this much. Generally, the vertical velocity is very small compared to the horizontal velocities like u and v. Compared to the horizontal components of velocity, which are u and v, w is having very less scale. It is of the order of centimeter per second. It is very less. This is just an imaginary question. It won't be this much vertical velocity won't have. So I think it is clear. We learned 3 different levels in the atmosphere, namely lifting condensation level, now we know what is Brunt-Väisälä frequency n, which is given by root of g by Tv into gamma v dash minus gamma v, and when n is greater than 0, it is stable, n is less than 0 is unstable. And then after the Brunt-Väisälä frequency, yeah, like in terms of gamma v prime and gamma v also, we learned how to define the conditions in terms of temperature of the parcel and temperature of the environment. Also we know how to define the different conditions. Then we learned about three different levels in the atmosphere, which is lifting condensation level, level of free convection, level of neutral buoyancy, and we learned two different energy terms, which is CAPE, which is nothing but convective available potential energy, and then we have SINE, which is convective inhibition energy. Higher CAPE and lower SINE is a condition for the development of thunderstorms. So what does CAPE is a positive? So if we take the curve like this, this is environmental latch rate, this is SINE, and this is CAPE. This is SINE, this is CAPE. And these are three different levels. This is LFC, this is LCL, this is LMP. Okay, I think it is clear. This is very basic things that is important to remember and understand these concepts clearly. So now let's consider three different cases. Like, let us consider three different air parcels. Consider three different air parcels. In the first case, in the first parcel, the parcel at the surface is having a mixing ratio. Mixing ratio is what? mv by mv. Mass of vapor to the mass of dry air. A mixing ratio, it just shows how much water vapor is present in the parcel. So it is having a mixing ratio of 1 gram per kilogram, which means for every 1 kilogram of dry air, there is 1 gram of water vapor. So this is first 11 gram per kilogram of mixing ratio. And there is a second parcel. Again, at the surface, the parcel is having a mixing ratio of 14 gram per kilogram. Now the third case, for the third parcel, the mixing ratio of the parcel at the surface itself is equal to its saturation mixing ratio, which means the parcel is already saturated. At the surface itself, the parcel is saturated. So how will the respective profiles for these parcels look like? This temperature, this is environmental lapse rate. So in the first case, the parcel is having a mixing ratio of 11 gram per kilogram. The parcel rises. Initially it reaches the level of LCL. At this level, the parcel will become saturated with whatever moisture content it already has. So 11 gram per kilogram the R will become saturation mixing ratio. R will become RS, and then condensation starts to begin. The temperature slowly starts increasing, and it will exceed that of the environmental temperature above LFC. So this is the first parcel. Now we have the second parcel. The second parcel is having a higher mixing ratio compared to that of the first parcel, which means it will reach saturation at a much lower level compared to that of the first parcel because it has a higher mixing ratio. Since the parcel has a higher mixing ratio compared to that of the first parcel, it will reach it will become saturated at a lower height. So suppose Z2 is the height at which the first parcel is reaching saturation, and Z1 is the height at which the second parcel is reaching saturation. Z1 is the LCL corresponding to second parcel, and Z2 is the LCL corresponding to first parcel. So Z2 will be greater than Z1. So the second parcel will reach saturation at a lower height compared to that of first parcel because it has a higher mixing ratio. And then again the same process, condensation starts to begin, and then it will reach LFC and eventually rise above it. Now in the third case is the parcel's mixing ratio is already equal to saturation mixing ratio. So the surface itself is the lifting condensation level for the parcel. So after rising to some particular, once the parcel is reached, condensation starts to begin, and then it will have the value of LFC at a much lower height compared to other two parcels. So in the first case, this is the sign. This is the area of the sign, and this is the area of the cape. This is having the sign area of the first parcel is greater than, if you look at the second parcel, this is the area of the second parcel. This much only is coming. Since it had a higher mixing ratio, it reached saturation earlier than the first parcel. So this is in case of second parcel. So this is less than the sign of air parcel 2, and there is no sign for third air parcel because it is LCL is at the surface itself. It is already saturated. So sign 1 is greater than sign 2. Now if we look at the cape, so this is the cape in case of the first air parcel, cape 1, and this area is the cape of the second air parcel. It is much higher than the area of the first air. This is for the second air. So this is cape 1 is less than cape 2, and in the third case, when the parcel was already saturated at the surface, this is the area. This is the largest. So that is greater than cape 3. So cape 3 is the largest, and sign 1 is the cape 3 is the largest, and it doesn't have a corresponding sign area, and cape 2 is coming in between. Cape 1 is having the lowest area, and sign 1 is having the highest area. So the formation of thunderstorm is more probable in the third case, like when the mixing and second comes the second parcel, and least probability is for the first parcel. And when you look at the LCL, the lifting condensation level in case of the first parcel is greater than the lifting condensation level in case of the second parcel, greater than the lifting condensation level in case of the third parcel. Okay, I think it is clear, and we are considering different air parcels with different mixing ratio, how the cape and sign areas are changing, and how the height at which lifting condensation level is happening is changing. Okay, so yeah, that's it. And I already told you, so how does we reach the lifting? So since I told you sign is a negative area, the convective inhibition energy is negative. The parcel is having a temperature of the parcel is less than the temperature of the environment. It is not self-buoyant. The parcel is not self-buoyant. So there is some external energy supplying, external agency is supplying the energy for the parcel to reach LFC. After that, it will rise on its own, because above LFC, temperature of the parcel is greater than temperature of the environment, and the parcel is self-buoyant. Now, what are the external agencies that provide the energy for the air parcel to rise till lifting level of free convection? So, the lifting mechanisms such as orography. So, if the air parcel is coming due to the orography, it will rise. First thing, and if there is low level moisture convergence is happening, low level convergence is happening in winds, then it will, the parcels will start moving upward. Then if there is local heating happening over a region, then also, because the parcels will become warmer, then it will become lighter and it will start rising. So orography, convergence, convection due to solar heating, local heating, and we have also seen frontal mechanisms we have discussed in previous slides. So these are the different lifting mechanisms that are there, which initially help the air parcel to reach till level of free convection. Okay, I hope it is clear. So now we will just do one more thing. So the Brent-Weissler frequency that we learned, we know what is the Brent-Weissler frequency in terms of lapse rate. The n is nothing but root of g by tv into gamma v dash minus gamma v. This is in terms of lapse rate. In terms of temperature, it will be root of g by tv into tv minus tv dash. This is in terms of virtual temperature. Now let us see, let us derive Brent-Weissler frequency. Brent-Weissler frequency in terms of potential temperature. What is potential temperature? Potential temperature is the temperature that an air parcel will reach if it is adiabatically expanded or compressed to a standard pressure level, which is generally taken as the surface pressure level or 1000 hectopascal. So theta is given by T into P0 by P, the whole raised to R by Cp. So theta is the potential temperature, T is the actual temperature, P0 is the standard pressure level, which is generally taken as 1000 hectopascal. Standard pressure level, and P is a pressure level at which the parcel is there. And R we know is the specific gas constant. Cp is the specific heat constant at constant pressure. Since we are considering moist air parcels, we will make everything virtual. So theta V is equal to Tv into P0 by P, the whole raised to R by Cp. Now, if we take logarithm on both sides, it will become, so we have theta V is equal to Tv into P0 by P, the whole raised to R by Cp. If we take logarithm on both sides, it will become log theta V is equal to log Tv plus R by Cp into log P0 minus R by Cp into log P. If we take logarithm on both sides, it will become like this. Now, if we will differentiate on both sides, it will become differential of log theta V is theta d theta V by theta V is equal to dTV by dV plus this is basically P0 is also constant. So the differential of a constant will become 0 minus R by Cp into dP by P. We will get this once we differentiate on both sides. Now we divide both sides by dz. Divide both sides by dz. If we divide both sides by dz, it will become 1 by theta v into d theta v by dz is equal to 1 by tv into dtv by dz minus r by pcp into dp by p. So we divided both sides by dz. Now this can be simplified after substituting dTV by dz. The rate of change of temperature with respect to height is nothing but the lapse rate, environmental lapse rate gamma V, and P is equal to rho RT, that we can substitute in the third term, and here dz, and dP by dz is equal to rho G. This can also be substituted in the third term. So in the second term, in the right hand side first term, replace dTV by dC by dz by gamma V, and in the third term replace P with R rho RT and dP by dz with minus rho G. It will become 1 by theta V d theta V by dz is equal to 1 by Tv into gamma V minus R by rho RT into Cp into minus rho G. It will become 1 by theta V into d theta V by dz is equal to 1 by Tv gamma P. So since this is dTV by dz will be negative, so we can write, because the temperature will decrease as we move up in the atmosphere. Right? So dTV by dz will be minus gamma V. So here it will be minus gamma V dV minus gamma V. So it will be minus gamma V by TV minus R and R will be gone. Rho will be gone. So it will be minus into minus plus G by Cp into dV. What is G by Cp? G by Cp is nothing but the dry adiabatic lapse rate gamma d. So 1 by theta v d theta v by dz is equal to, we take 1 by dv out, 1 by dv into gamma d minus gamma d. Now gamma v is the environmental lapse rate. Gamma v is the environment lapse rate and gamma d is the lapse rate of the parcel which is unsaturated, right? Gamma d is nothing but gamma v dash, or the lapse rate of the parcel which is unsaturated. Gamma d is equal to gamma v dash. Now we can rewrite this equation as 1 by theta v into d theta v by dz is equal to 1 by tv into 1 by tv into gamma v dash minus gamma v, right? It was gamma d minus gamma v dash minus gamma. Now initially I told you what is the equation of front Weissela frequency. N is equal to root of G by Tv into gamma V prime minus gamma V. So if we substitute this, we can write in terms of potential temperature, N is equal to G by theta V into d theta V by dz. Correct? So this is the equation of Brunt-Weissela frequency in terms of potential temperature. Brunt-Weissela frequency in terms of potential temperature. So what will be the, so we have already learned N is equal to positive only gives us real solutions, or this basically implies stable conditions. So if N should be positive, which means d theta V by dz should be greater than 0. There should be an increase in potential temperature with respect to height. Whereas N is negative, it will basically lead in imaginary solutions, which means the frequency is imaginary, which means the parcel will displace and the will keeps on moving in the displaced direction. So N is negative. This is basically unstable condition, which means d theta V by dz is less than 0. If the potential temperature is decreasing with respect to height, it means there is an unstable oscillation, or the condition corresponds to unstable condition. Okay. Now we will try to solve one problem. If the potential temperature of an environment is increasing at the rate of 3 Kelvin per 100 meter, 3 Kelvin per 100 meter, the potential temperature of the environment is 20 degrees Celsius. What will be the frequency of oscillation of the parcel in the environment? Frequency of oscillation of the parcel. So what all things are given? If the potential temperature of an environment is increasing at the rate of 3 Kelvin per 100 meter, potential temperature of the environment increasing with respect to it, d theta v by dz is given, which is positive and is having a value of 3 Kelvin per 100 meter or 0.03 Kelvin per meter. And the potential temperature of the environment, theta v, is also given, which is 20 degrees Celsius, which is basically 20 plus 273, 293 Kelvin. And then what will be the frequency of oscillation? We have to calculate n, the Brent-Weissler frequency. N is given by root of 1 by theta v into d theta v by dz, which implies root of 1 by 293 into 0.03. So this is Kelvin, G by 9.8. G is also there, right? So G by 293 Kelvin into 0.03 Kelvin per meter. 9.8 is having a unit of meter per second raised to minus 2. So final answer will be in the unit of second raised to minus 1. So how much it will be? Can you calculate and tell me what will be the Brent-Weissler frequency in this case? Any answers? How much it will be? .8 into 0.03 divided by 293 and whole square root of. So the value will come around 1.003 into 10 raised to minus 3 second raised to minus 2 square root of this, which will become 0.03 second inverse. This is a frequency of oscillation, right? Yes, 1.0016 into 10 raised to minus 3. That is, you have to find the square root again. That is the value of n square. We need n, so root of that answer. Final answer will be 0.03 second inverse, right? So this is basically the frequency of oscillation. Now, if you want to find the period of oscillation or the time that the parcel takes to complete one oscillation, Period of oscillation is basically given by T is equal to 2 pi by frequency. So it will be 2 pi by ns 0.03 second inverse, right? 0.03. So how much seconds it will be? Can you tell me? What will be the period of oscillation of the pulsar? Yeah, 209. It will come. 209, 202. Kind of like that. Around, yeah, 209 to near to 200 some value you will get. 202 kind of something. So this is in seconds. Now if you want to calculate it in minutes, how much minute it will be? 202 divided by 60. It will be around 3 minutes approximately. So yeah, so that is a very relation of the air pass. I think we will end it here today. Just if you have any doubt, you can ask me regarding the concept of stability. What are the different conditions for stability in terms of the lab state, in terms of temperature, and in terms of the Brunt-Weisela frequency we have learned. We also learned what is the uh, two different energy criteria like convective available potential energy and convective inhibition energy. We also learned what is conditional instability when the lab state of the environment is actually coming in between the dry diabatic lab state and the saturated diabatic lab state. That condition is basically known as conditionally instability or conditional stability. Yeah, so these things also we learned what is convective available potential energy, what is convective inhibition energy. Mm, Then we learned this. Finally, we learned about how to derive the Brunt-Weisela frequency in terms of the potential temperature. So we know what is the equation for the Brunt-Weisela frequency in terms of lab state, in terms of temperature, and in terms of virtual temperature, and finally in terms of potential temperature as well. Okay, I think that is enough for today. We will conclude the class here. If you have some doubt, you can ask. Or else, thank you for joining. Bye. Thank you.